everybody. I'm Pete. So who's excited for some big O notation in the morning? All right. So we're going to get to that. But before we do, I'm just going to say I'm Pete. I work at Facebook on the Instagram team, and I'm a contributor to a library called React, which you may have heard is the one that puts the angle brackets in your JavaScript. But I'm not going to really talk too much about React and why it's so awesome, because that's not the interesting part. What I want to talk about is the ideas behind React, and React is the reference implementation of those ideas. So this isn't a tutorial, and we're going to focus on ideas, not implementations. So I'm going to talk about some of the ideas behind React, some of the ideas behind other systems, how they're different, kind of what the different trade-offs are, and there are different trade-offs between them. And hopefully you can take some of the ideas and bring them to your favorite system, or maybe you think that React is cool and you contribute to it. But let's talk about what makes user interfaces difficult to build. So has anybody here built a user interface before? All right, okay, I figured. Was it really easy? Yeah, testing it was super easy. Maintaining quality was probably a joke, right? It just kind of always works. He said sarcastically. But you get this a lot. It just doesn't feel right. So, even if you use all the test-driven development that you can throw at it, you still have to have a human look at this and be like, this doesn't look right, or this doesn't feel right, or when I click this button, then I click this button, then I click this button, it breaks. So there's a lot of things that come into this. They are human verified, but UIs are also deceptively complex. We have a bunch of designers who focus exclusively on making UIs seem simple, but underlying that simplicity is a lot of complexity. There's a lot of state there. And the tools that we have today aren't, there's some pointing over there, I don't know. But there's a lot of, your traditional unit testing, for example, it helps in UIs, but it doesn't really, solve a lot of the problems that it does in the back end. Static analysis tools, too, they're helpful, but they don't really they don't prevent you from, or they don't replace the human in the loop. But at the end of the day, UIs have a lot of complexity. The good news is we're programmers, and our job is to organize this complexity. Dijkstra said the art of programming is the art of organizing complexity, of mastering multitude and avoiding its bastard chaos as effectively as possible. Now, isn't everybody just amped up right now to go build some UIs? Come on. I like to focus on being predictable. And another word for being predictable is to be reliable. So it's really hard to build UIs. I would just prefer if they broke the same way every time. And if the same series of interactions that a user does, if I do it on my workstation in my development environment, I want it to have the same behavior. So let's talk about how we make UIs a little more reliable. Data binding is what we do today. Has anybody here used data binding before? Okay, cool. So Dijkstra is a really smart guy, and I think he came up with data binding back in the 70s. Because he said we should do our utmost to shorten the conceptual gap between the static program and the dynamic process to make the correspondence between the program and the process as trivial as possible. What does this even mean? Data binding makes the UI, which is a dynamic process, look like a static program relative to this other dynamic process, which is your kind of business logic and your fundamental interactions. The TLDR here is that it syncs some state in one place with the state of your UI. Everybody buy that who uses data binding? Seems reasonable? So the way I look at data binding is that it's a polyfill for reactive JavaScript in the DOM. So if we want to sync state between different parts of your program, one of the solutions to that is something called reactive programming, which is basically expressing your constraints, and then the data is always guaranteed to be consistent where you expect it to be. Now, unfortunately, JavaScript isn't actually reactive, so we have to build an abstraction on top of it. And because this is definitely a non-trivial abstraction, every data binding technique that we have, including the virtual DOM, which is the one that React implements, is leaky. Let's talk about simplicity. So we had a data binding system at Facebook a couple of years ago called Bolt, and we used a traditional kind of observable data binding approach. we found that it was very difficult for us to understand what was happening specifically in our ads products. So there were maybe 2 people at the company that if they got hit by a bus, no one would understand which order the events would fire in and couldn't keep the UI consistent. So we wanted to find a solution that was simpler and easier for people to understand what was going to happen. That is, something that was more predictable. Dykstra, man, he just has so many great quotes. Simplicity is prerequisite for reliability. So if we want to make this reliable user interface, we need to focus on simplicity. Now, simplicity is one of these loaded terms that everybody throws around, and it feels very subjective. What's simple to me, maybe it doesn't seem simple to you, or vice versa. But there's actually an objective way to look at it. And it's the definition of simplicity I'm going to be using throughout the rest of the talk, which is marked by the lack of interleaving. So Rich Hickey gives a great talk called Simple Made Easy. He's the guy who invented Clojure. And he focuses on a couple aspects of simplicity versus easy. And simplicity is marked by the lack of interleaving. And what's important about this is that when you want to go and solve a problem when you're programming, you need to basically page in all this information into your brain. And the less stuff you have to hold in your brain, the easier it is to solve a problem. So if we try to just purge all of the interleaved concepts in a given piece of code and separate those out, separate those concerns, if we want to solve a problem with a piece of code, we don't have to load in all those interleaved concerns into our brain. It's important to keep in mind that simple is not equal to familiar. So as we examine some systems, whether you're familiar with it or not, let's try to look at it in terms of interleaving of concerns rather than whether it looks familiar, feels familiar, or the API looks good. So the most popular way that we implement data binding today is something called key value observation. And this is pretty much everybody but Angular, and on different platforms as well. So .NET implements this, Core Data implements this on iOS. And it's built around the idea of observables and computed properties. Now later today there's going to be some talks on RxJS, and they use observables in a different way. I'm thinking about this more in terms of kind of a knockout or Ember-style observable. So let's walk through an example of how we would build an application. Let's say we get some JSON from the server, and we're going to build like a Rotten Tomato for businesses application. So we've got titles, number of upvotes, and a number of downvotes, and let's say we have a couple hundred items in this array. We want to render a UI that looks like this, and our designers are very talented, by the way. We have the name of the company, and then we have the percentage of votes that are upvotes, and we sort them by the total number of votes, not the percentage of upvotes, the total number of votes, and we take the top 3. So we're basically showing, here are the 3 most popular companies, and here are their ratings. So again, I'm going to focus on ideas, not implementations. And so I want to really look at key value observation right now. And if I want to think about kind of the premier way to implement KVO on the web right now, I would say it's probably Ember. This team is focused a lot on developer experience. They've built a lot of applications, and they're starting to focus a lot on performance as well. So the way I look at it is if Ember can't get KVO simple, who can? So this is the template, and it's implemented in handlebars. And we basically iterate over every one of the top companies, and we render a title and a score into the DOM. Now, if we want to bind anything to the DOM in Ember or in any of these other sort of traditional KVO data binding systems, we need to have some sort of template-like thing that provides a DSL for gluing some observable to a DOM node, and that's what we're doing here. So obviously, this isn't expressive enough to build our entire application because we're limited to some primitives like each, and we don't have kind of the complex tool set that JavaScript gives us. So we write some code on the back end of the front end that implements this functionality. So I want to compute the total votes of a company, so I use a getter or I use 2 getters to get the upvotes and the downvotes, and I sum them. Then I model the company as an Ember model, and I want to compute the score. This is called a computed property. So what this is doing is this is taking the percentage of the total votes that are upvotes and rendering it as a percent. So this is what the toFix does and multiplying by 100. Now, it's important to look at this dot property syntax. What this is saying is whenever the upvotes or the downvotes change for a company, make sure that the score is automatically re-rendered. So when we render the score into the DOM, it will track the changes. If I change an upvote, it will make sure that that DOM node is kept up to date because it maintains a representation somewhere in the internals that maps all of that stuff together. So if you remember in the template, I iterated over something called top companies. This is another computed property where I sort by the total number of votes descending, slice off the top 3, and whenever the array of companies changes, we want to update that sorting. So imagine we have kind of live updated upvotes here. So we might need to resort when a new company is added, or we might want to resort when somebody votes on something. So the top 3 that are shown could change at any time. And the last step is we just glue it into our data model. So I have this get companies JSON function that is standing in for that JSON document. And that 100 is just the number of companies. So does this code look good? Pretty happy with it? I'll take your silence to mean let's push it to production. All right, great. So here's a video of it in action. And I'm updating the votes randomly every second. And because I'm updating the number of votes randomly every second, simulating like WebSocket pushes or server refreshes, you would think that this would be resorting. Let's run it again, if I know how to use Keynote. Yeah, so the top 3 shouldn't be the top 3 throughout this entire video. They should be resorting all the time. Ooh, so where's the problem? It's right there. So in a KVO-based system, you need to tell the system, update the top companies whenever this company's array changes. Now the problem is we're not actually observing changes of the items within that company's array. So we have to change this to read like this. And this is a domain-specific language for specifying observation. Now the problem is going back to reliability from simplicity, and simplicity is lack of interleaving and how much stuff you need to hold in your head. How am I supposed to know that I have to write those in this function? Because if I look at top companies, I don't see those upvotes or downvotes anywhere. I have to actually know the implementation of total votes and keep that in my head as I write my code. So when I apply this fix, it resorts kind of as you would expect it to. So I get the feeling that there are a bunch of Ember fans here. And they probably spotted that bug early. And they said, you shouldn't have total votes as a function. You should have it as another computed property. And they're right. But the way I look at it, this is a problem that we shouldn't have. Ember says that you're not allowed to use functions to compose your programs anymore. And this isn't a limitation of Ember. This is a limitation of key value observation because the language doesn't support true reactive programming, and this is a leak in that abstraction. So you have to use units of composition that the observation system gives you. So there's a lot of criticisms of this model, and Angular tries to solve that using something called dirty checking. So let's build a different widget. This is a unit that we have on Facebook all the time. It's a profile picture with a username next to it, and we want this component to be reusable and live updating if there were interesting pieces of data in there. So in Angular, this is kind of an Angular-specific thing, a little less related to data binding, but this is how you would specify, I want to render this avatar in my page. Looks pretty good, actually. Let's go through the code that we need to write in order to build this. So we'll start with a little bit of boilerplate, setting up this scope, and scope is how you pass data between directives and controllers in Angular. And what Angular will do is Angular will watch that scope variable, and when changes happen on that scope, it will re-render for you. So if I want to build my FB avatar directive that I showed you in that previous slide, I want to actually use composition here, and I might have like a face pile in the right-hand column of Facebook.com where I only want to show profile pictures. So I should be able to reuse that component in multiple places. So I compose the avatar out of some HTML and this picture component or directive. And if I want to describe that picture directive, this is how I implement it. Now again, you'll notice that because we're using data binding here, I can't compose with my regular primitives that JavaScript gives me. I have to do this scope user equal thing, and there's like a bunch of different ways that you have to tell Angular, hey, this is how I want to pass my data. And you still have problems with deep observation. So it only, if we want to actually observe changes in the username and the full name, we have to set up we have to change the way that scope works. So we can build complex performant applications using KVO or dirty checking. But I don't think it's the simplest way to build things. And again, we've got like Google, are they one of the most premier web companies out there? And Ember is focusing so hard on making this easy to use and getting successful. And I don't think that they've come up with simple tools. So let's see if we can build a better abstraction. And we'll start by kind of thinking about what is our ideal system. So if we had a really talented engineering team and we wanted to build an implementation of JavaScript that was reactive, what would that look like? Let's go back to this example. So we'd start with some code that looks like this. Now remember, with the Ember example, we needed to use a domain-specific language, handlebars, to glue this data model to your DOM. So let's use JavaScript and say, hey, render component, and then we'll do something in this function in a second, but put it into the document.body. Specify that binding in our reactive JavaScript mythical language. If I want to compute the total votes, I just write a function that computes the total votes. And the runtime will track all those changes for me in this mythical reactive JavaScript language. Then we'll render a UL, an unordered list element, with our factory functions. Now, normally that would be document.create element, and you pass it the string UL. But just for the sake of this example, I don't want to write all that code. And then we'd sort the list of companies by the total number of votes, just like we did in the previous example. We'd slice off the top 3, and then we'd map over each one, and we return a list item, and we'd have this inline expression here that computes that percentage votes, or the percentage score. What's important to note here is that I'm just using JavaScript primitives here, and because we've implemented this reactive JavaScript mythical implementation, it all just kind of stays up to date. And that means if you don't like the way this code looks, you just refactor it like you refactor any other piece of JavaScript. So let's say that we don't like that inline expression right there. We can do it because we don't have to use a helper or a computed property for it. But if we want to move it out, we can just make a function and move that code around. And at this point, we can actually unit test these components separately. So if we want to do more of an integration style test, we test render app. But if we want to test just how the rows render, we can test that specifically. So we can't do this today because we don't have a reactive JavaScript implementation. Man, I jumped ahead of my slide. That's the first problem. The second problem is that the DOM is stateful. If anybody's done game programming before, you can think of the DOM as a retained mode rendering engine. So we do actually need to build some layer of abstraction on top of this. But we'd like to build one that gets as close to that example as we can. So we built a virtual DOM, which I think is a less leaky polyfill for reactive JavaScript than the DOM. So the good news is this is actually valid React code today. And it's important to remember that while this might seem unfamiliar, there's no data binding artifacts here. You don't even have to think about kind of your data dependencies because it solves them for you using the same tools that you already have today in JavaScript. And it can take advantage of like 50 years of programming language research if you think JavaScript took advantage of this. I actually do, but imagine trolls trolling me on Twitter for that. So how would we implement this if we can't build our own JavaScript VM? Well, we want to use the tools like the full power of JavaScript within our applications. So we treat the user code as a completely black box, where there's a signal that says, hey, something in your application may have changed. And we run your code, and then we only look at the output. So whatever you do inside of this black box is completely up to you. And whenever we re-render, we take your return value and we diff it with the previous return value using a set of heuristics that we've come up with. And we only update the real DOM with what actually changed. And a lot of nice things fall out of treating user code as a black box. Not only do you, because you avoid interleaving this observable abstraction with your code, you can get a lot more expressive power. And this is the kind of textbook definition of expressive power when applied to programming languages. And I don't think it's actually the exact definition that I'd like to use for data mining, because you can build the same applications in a virtual DOM system that you can in a KVO system, that you can in a dirty check system. But practical expressivity is a subset of expressive power, and it means how concise is it to express those concepts in that system. So how often are you fighting the framework or the language or whatever? But the reason I think people are doing data binding right now is because they think that re-rendering and diffing is expensive. And kind of intuitively, it seems like that would be expensive. You know, whenever something may have changed, re-render everything and then do an O of n walk through that result. Like, that just seems like a lot of unnecessary work. This quote's actually about Lisp programmers, but JavaScript's kind of like Lisp. I don't know. Programmers know the value of everything and the cost of nothing. So it's true. With a KVO system, you're doing a lot less recomputation of things that you don't need to compute. But there are downsides. So KVO does entangle your app code with observables, and Angular-style dirty checking is similar in that you have to pass everything through scope in order to get those automatic updates. And the leak with virtual DOM is that you need a signal somewhere that says something may have changed. So because of some performance characteristics in the ClojureScript programming language, their bindings to React, which is our reference implementation of virtual DOM, use request animation frame as that signal. So it's kind of invisible. But it could be any user event, server response, object.observe if you want. But most data binding systems aren't actually statically analyzable. This is another constraint to these systems. So anytime you put a JavaScript identifier in a string, all of that tooling that you can use for statically analyzing JavaScript, so think JS hint, TypeScript, Google Closure Compiler, advanced mode, they don't know whether that string represents an identifier or like a user string. So they can't do all that analysis that they normally can do. And they can't minify it as well. So we've talked about the costs here, but it still seems like a KVO system would be the most performant way to build these user interfaces. But like anything, there is a nuanced set of trade-offs. And the one that most people overlook is memory, actually. So there's a lot of focus on benchmarks and CPU, but on mobile, if you burn a lot of CPU, you might burn through their battery a little bit, but your application still works. If you burn through too much memory, iOS is going to kill your browser process, and you're just not going to be able to use the application at all. So keep that in mind as we start thinking about performance. So yes, KVO basically triggers a callback and then recomputes only what needs to be recomputed. But you have to maintain a representation of that dependency graph. So you need to know when a computed property needs to change relative to another computed property or observable. And there's a cost to that in CPU and memory. With a virtual DOM approach, one observation we made is that render code is actually very cheap. So if you think about the types of logic that you write in your UIs, there's usually very few, if any, really tight loops, and that's normally where your performance problems will come into play. Again, these are kind of usually we have found like kind of hand wavy, but just think about examples in your own work and see if this is true or not, because a lot of the intuition that we've had is based on experiences we've had building applications. And another thing we observed was your view is usually smaller than your model. And if it's not, you don't normally have performance problems. So think about the types of things that are historically performance sensitive. Giant infinite scrolling data tables that are sortable by whatever column you want, or type ahead searches tend to be the things that we care about performance on the web. And those have a lot of data, and they don't actually render that much of it. And this example is a perfect example of that. There's actually any number of companies underlying this user interface, and we're only showing 3 of them. Nice, they laughed. Great. So I'm going to show some raw performance benchmarks. Remember, this talk is about ideas, not implementations. And this is going to be used as evidence of the order of growth of performance of these systems. So I'm going to try to make it clear that there's like kind of order of magnitude differences, not like, oh, we're 3 milliseconds faster spinning balls on JS Fiddle or something. So that previous example where we're rendering the list of companies and we show that percentage score and we take the top 3 and we sort them. When we have 25 items, the KVO example are numbers from Ember, and the virtual DOM is numbers from React. You'll see that it doesn't really matter what technique you use. These are, for all intents and purposes, the same. But when you bring it up to 10,000 items, you start to see pretty significant differences in performance. And I would say that these differences are big enough that it suggests like a fundamental performance trade-off with the underlying ideas rather than the implementation itself. And the reason for that is O of n. What do I mean by O of n? Big O notation is a way of expressing how the performance of an algorithm, or what the performance characteristics of an algorithm are. But it matters a lot what n is. So let's break it out into O of v versus O of m, which is the size of your view versus the size of your model. And in our observation, the performance-sensitive apps have v, which is a lot smaller than m. Again, those performance examples are like type-ahead search, sortable data tables, timeline on Facebook as well. So if we were to look at those systems in big O notation, we would see that on a single update, your intuition is correct. Like a KVO system triggers a single callback and then computes only when it needs to recompute, and it's basically a constant time operation. Whereas for a virtual DOM system, because we have to diff everything, that diff is linear time, so you have to diff everything in your view. But the big win with memory is that a virtual DOM system only keeps track of what's actually rendered, whereas a KVO system has to keep track of everything in your model. So if you want to sort a long list, like you have to build this giant data flow representation in the implementation. So obviously I have some bias because I work on a virtual DOM system, but let's look at the worst case scenario. Again, we're talking about diffing these 2 kind of opaque data structures, and if you're only changing one tiny little thing in this giant haystack of DOM nodes, you would think that that diff would be a lot of wasted effort because you have to render it and walk through each item. And your intuition would be correct. If you look here, for this warm update, this needle in a haystack thing, you'll see that KVO system Ember is sub-millisecond. It's just a callback and a DOM manipulation. It doesn't get much faster than that. Whereas virtual DOM system has to diff all 10,000 of those DOM nodes, and it takes around 40 milliseconds. And I think that I've constructed like a pretty pessimistic use case here. Like this is a pretty big DOM, and I haven't seen, you don't see this kind of scenario very often, so normally this doesn't bite you. But let's say that you're in this scenario. When you normally try to solve performance problems with data binding, the instruction manual says, like, do it manually and break out of the data binding abstraction. With virtual DOM, because this is just JavaScript and your implementation is a black box to us, you would just solve it the same way with you would in JavaScript, which is caching or memoization. So with our reference implementation, React, you can provide a hint to the system that says, hey, cache the results of this component. And it looks something like this. So in our example, if we had tons and tons of companies, and we were rendering all of them into the DOM, like in this example, we would just add a hint to each row of the list. And we would say, only diff or only render and diff this subtree or this row if the upvotes or the downvotes have changed. And we have profiling tools to help you create those. So when we apply this hint, you can see with the optimized virtual DOM, we can get it down to 7 milliseconds, which, by the way, is 10 times slower than KVO. But it's still within a single request animation frame. So this isn't user perceptible because the browser literally will not paint faster than this operation occurs. And this is a kind of worst case scenario for virtual DOM. So think about all the performance and usability trade-offs that I've talked about. We can get lower memory usage, and we can get, if you're windowing, basically only rendering a small part of your data. And it's a lot more expressive, in my opinion. And what you lose is you don't even lose a full frame when you have to apply this optimization hint, which, granted, is a leak in the virtual DOM reactive abstraction, but it's a leak that you can apply at the end after your application is already built. And tooling can help you with it very easily. So my friend who works on Ember performance says, if you're going to keep making the performance argument, you'll eventually lose. And this is true. And Ember has been my example here, but they're making great performance strides, and the next version of their templating system is going to be really fast. But I think that ideas have fundamental performance properties. So the secret of the virtual DOM, so to speak, as tacky as that is not about performance. It's about simplicity. If you want to build sophisticated applications, sophisticated, reliable applications, they need to be simple. They need to be built on simple, composable primitives. And I'll make the argument that because of its simplicity, a virtual DOM-based system is the most expressive way to build user interfaces in JavaScript, bar none. It's the difference between writing some regular JavaScript and writing a bunch of stuff that explicitly needs to deal with observables and data binding to the DOM. And you're not allowed to use functions. And it's the difference between composing with these sorts of primitives and these sorts of primitives. And you can see these in kind of order of magnitude lines of code. So if you want to use Firebase, which is a real-time database, it's like 300 lines of code to build bindings to these systems. With a virtual DOM system, it's literally pass the data model in, and because it's a black box that doesn't know about observables, it just works. It's like 10 lines of code. So performance isn't the main goal. But if you're worried about performance, most workloads are as fast or faster out of the box. And in the worst case, you add an optimization hint, and you can get within one frame without completely breaking out of the abstraction. So I urge you to not trade simplicity for familiarity. Thanks.